Can all of you hear me? Yeah. All right. There is no quiz or test or anything today. Okay, so today is the only Thursday where we have nothing to do. We have test one next week, which will cover everything that we do in sections 1.3 and 1.4. Okay, so we'll finish off that today, and then we'll probably start chapter 2 slowly, but that'll be for test number 2. Okay. All right, before we start, do you have any questions about anything? I think I had one more problem remaining in that handout regarding the mixing problems. Okay, so let me just quickly talk about mixing problems, the setup and everything, and then we will do that example. Okay, so point 4. We have a tank which initially has some kind of liquid in it. Could be a solution or could be pure water. Okay, and there is something coming in which could be again a solution or pure water. So we define C to be the concentration of salt in the incoming solution. Okay, water coming in, and R is the, well, I shouldn't write in there, concentration of salt in water. R is the rate of flow, okay, which is volume per time, that is mass per volume. Okay, and then depending on whether it's coming in or going out, we could define C in, C out, R in, and R out. And if A of T is the amount or the mass of salt in the tank at time T, then by the law of conservation of mass, you can write the rate of change of A with respect to time is rate which is coming in, okay, minus the rate that is going out. Nothing is created or destroyed by itself. Okay. And I think based on all the examples we saw yesterday, okay, this is a given set of numbers. You don't have to worry about those. In general, C out is something we don't know. It is the concentration of the outgoing solution. So we need to know how much mass of salt is there coming out. So that is the unknown here. V is the volume of the solution in the tank, which will change if the rate in and rate out are different, and that is given by dV dt equal to R in minus R out. If those are same, then the volume is fixed, right? If it is not the same, the volume will keep changing with time, and this will give you V of T equal to some function of time plus C. It's going to be a linear function because this is a number, okay, plus C, and the C is always equal to the initial volume. And then once you have that, you rewrite this in the standard form, dA dt. So bring this to the left-hand side, you get A over whatever V you get from here, okay, times R out, which is a number, equal to C in R in, and we also need the initial amount of salt in the tank to solve the initial value problem. Okay. So this is usually given in the question. That will help you find the value of C when you do that solving using integrating factor. And you should see that if C in is equal to 0, this is a separable equation. Okay, so in some cases the question can be a lot easier than what you think. If the solution coming in is just pure water with the impure thing in the tank. Okay, then C in would be equal to 0. In that case, we have a simple separable equation. But in general, you need integrating factor to solve this. All right, so let's just do that last problem in your handout. Okay. So handout, it's on Canvas. I just added another handout today, so you have to look at the one with the mixing problems. Okay. Problem number 4. It's a little bit more intense than the third one. The third one we did yesterday was not too bad. This one is a little bit tedious. So can you start doing it? I hope all of you have access to this file I'm talking about. Okay. Too many windows open here. Let's see. Those of you who are online, I'm talking about this thing. All right, so let's start populating these values here. So C in so I hope all of you are comfortable with these notations. So C in looks like 2, R in is 7, and R out is 5. And it says that the tank is half full of pure water. So the fact that it's pure water inside the tank should mean that A of 0 is 0. Okay. And since it's only half full, the initial volume is going to be 50. Okay. So it clearly shows that you have to read the question and not just look at the numbers and start writing it down. Okay, so dA dt is C in R in, which is 14, minus C out, which is an unknown quantity here, and R out is 5, where dB dt is R in minus R out, which is 2. So V is 2T plus C, and since you have V of 0 is 50. Volume as a function of time is 2t plus 50. Okay, so it kind of looks very similar to what we did in example number 3. Okay, except that unfortunately this term here is an odd number. There is not a lot we could do with it in terms of canceling things out. Okay. Yesterday we had a 2 there, which kind of conveniently canceled out this 2. So the remaining steps were rather easy. Here you have a 5, so the next step is going to be a little bit more intense. Okay. Not too bad. So dA dt, let's bring it to the left-hand side, plus 5 divided by 2t plus 50 times a equal to 14 with a of 0 equal to 0. That is the initial value problem you're trying to solve here. And just like I told you yesterday, it will be nice if you factor out it 2. Okay, even if you cannot cancel anything, at least it will keep that outside of your integration part and not mess things up. So this is 2 times t plus 25. So your P of t is 5 divided by 2 times t plus 25. Yes, we need to find the integrating factor here. So the integrating factor I of t is e to the power of the integral of that term. Okay, the 5/2 can be pulled outside. You get 1 over t plus 25 dt. All right, so it's going to be e to the power of 5/2 times the natural log of t plus 25. I hope all of you remember how to do this simplification here. This will be what? T plus 25 to the power of 5/2. Not the most pretty looking integrating factors, especially if you look at example 3, just a more straightforward looking term, but that's okay. As long as you do it without making mistakes, you're good. So multiply this on both sides of the equation there, the standard form. Times the differential equation, which is a prime plus 5/2 times a, and by now you know why you're doing this. Okay, the left hand side is going to just collapse into a single term. The reason why I keep on multiplying this on both sides is to make sure that the right hand side is also done the same thing. Okay. So it's very easy to forget that part. If you just keep focusing on this side here and don't do anything here, then you'll just write 14. Okay, so it's 14 times the integrating factor. And because of our derivations we did the other day, I forgot when, t plus 25 to the power of 5 times a prime is equal to this. Integrate both sides. Times a equal to the integral of this with respect to t would be 14 times t plus 25 to the power of 5 plus 1 is 7 divided by 7 that's going to be times 2/7 plus c. So this is 4 and divide both sides by, I think you could find the value of c right here. Okay. So a of 0 is 0. So it's going to be, left hand side is just going to be 0 because you're multiplying 0 times something. Okay. And a of 0 was 0 because we had pure water in the tank. That's equal to 4 times this huge number, 25 to the power of 7 plus c. (25 to the 7 is the same as 5 to the power of 7, which I don't know what it is. And you have to then multiply it by 4 and negate it. Yeah. Can you just say the digits one by one? That's it? Oh. So I thought it's a huge number. Okay. See, it's negative, what is that, 3 million or 31,000? 31,000, no. 312,500. Need to know how to read numbers. All right. So then you could plug that in back into the solution and then divide both sides by t plus 25 to the 5 So a of t is 4 times. So when you divide t plus 25 to the 7 divided by t plus 25 to the 5 you get just t plus 25 minus this 3,125,0,0. That's a huge term that is pulling this backwards because this is a linear term. Looks like it's just increasing forever, but this is going to keep pulling it down. Okay. With an exponent of negative 5/2. So that you don't get an infinite amount of salt at the end. Okay. Once again, that is not the last part of the question, right? The question is asking you when the tank overflows and then what is it the mass or the concentration it's asking? Concentration of salt in the tank. And we did a similar problem yesterday, so I hope you know what to do here. The tank overflows when volume of the tank is equal to its full capacity. Full capacity in this case was 100 gallons, I think. And V of t was 2t plus 50, was it? equal to 100. So T is about to say 50, but it's 25. And the units would be minutes. Okay, so this is the part of the question where you don't need any calculus to do, right? All of us know when the tank overflows, the volume is the full volume. And now plug it into the solution that you got, A of 25. Make good use of your calculator. So it's 4 times 25 plus 25 is 50. So 4 times 50 is 200 minus that ridiculous number times 50 to the power of negative 5 half. And I want your help. Yeah. Exactly. 182.3. Was it given in pounds or grams? Ounces? Yeah. Okay, so that is a mass of salt. The concentration would be mass divided by the volume. Okay, the full volume is 100. So the concentration during the time of overflow would be A of 25 divided by the volume at the same time. And I don't think you need a calculator for that one. 1.823 ounces per gallon. Not very religious about units in this course, but if it is given, it's always nice to have an idea about what kind of things you're dealing with here. All right, so took us around 20 minutes to do it, okay, but that's also because I was kind of taking some breaks in between. But if you don't practice it, it's going to take a long time to do this problem. So please practice this ahead of time, not during the test. All right, so I think there are 2 problems assigned in the textbook, in the homework. One of them, I think, it's usually one of those questions that pops up during my office hours. It's asking for at what time. So this is one of the homework questions. Does something become maximum or minimum or something? The amount of salt in the tank becomes. And for some reason, this always throws the students off a little bit. So they know how to solve for A of t, but then I think one of the questions is at what time does it become maximum? How do we do this? Yeah, so this is just calculus 1. Okay, so just need to find its derivative and set this equal to 0 to find its critical point. Okay. Unfortunately, mathematics is very cumulative. So whatever you learn at one stage, it keeps popping up here and there. Okay. So that is, if you look at a solution, you would see that there is some kind of a random equation that I have written and set that equal to 0, and that is that derivative, okay, for that whatever is before it. So I hope it won't create panic waves during your practice. Apart from that, it's a pretty standard exercise if you do enough number of problems. Okay. Yep.
How would you solve it if they said that when the tank is full, the inflow rate would stop and then the outflow rate would become higher? Would you have to do 2 equations for A of t?
Yes. I mean, I think based on what he said, the answer is yes. It will. Yeah. But that's a lot more complicated than what we need to look at. All right, any other questions from the online community? Any issues, questions? see fewer people today. I don't know whether it's because everybody is exhausted by the end of first week. All right, let's take a look at a very special class of differential equations that can be solved using integrating factor. Okay. This is actually an extension of section 1.4. It's called Bernoulli's differential equation. I hope all of you have heard the name of Bernoulli, especially if you're an engineer. Okay, he was one of the pioneers of fluid mechanics, and also all the flight applications that happens is because of his theories in fluid mechanics. Okay. So the reason why your airfoil has the shape and there is lift when your airplane takes off, he was the pioneer who suggested that concept. Anyway, so he talked about a very special class of differential equations of this type. Okay. So if you have y prime plus p of x times y equal to q of x times y to the power of n. This is a nonlinear equation in general, right? Because you have this y to the power of n here. Okay. If n equal to 0, no harm. Okay, we are back to square one. Nothing happens. And if n equal to 1, it's linear. Okay. It's not only linear, we could also separate and solve it. Linear and separable. So when you say Bernoulli's differential equation, that is for cases when n is not equal to 0 and n is not equal to 1. What if n is not equal to 0 or n is not equal to 1? It could be anything else. It could be 5 or -2 or -3/7. Okay, who cares? Bernoulli suggested something very smart, actually, which when you look at it, it's pretty easy, but then somebody has to come up with these smart ideas. Okay. So Bernoulli's idea was this. Divide this y to the power of n throughout this equation. Now, in first look, that might look like a bad idea because you're creating a negative exponent sometimes, but let's see what he wants to do. So it's y to the power of -n times y prime plus p of x times. There's already a y there. Okay, so now you're multiplying a negative n to it, y to the power of -n to it. So it becomes y to the power of 1 minus n, because it's going to be this y times y to the power of -n equal to q of x. All right, it still doesn't look like you're getting anything. This idea was this. Let's just substitute u equal to this term. So let u equal to y to the power of 1 over n, 1 minus n. So we are going to convert this differential equation into something in terms of u instead of in terms of y. Okay. So let's try to find what du dx would be. Remember that u is a function of y is a function of x. Okay. So when you say du dx, you are doing chain rule, du dy times dy dx. Now we can find du dy here, okay, using calculus 1. Du dy would be 1 minus n times y to the power of 1 minus n minus 1. Which, typically you would do n x n minus 1. So it's 1 minus n y 1 minus n minus 1, which is equal to 1 minus n times y to the power of negative n, because this 1 and negative 1 cancels out, right? So your du dx becomes du dy, which you just did there, okay, 1 minus n times y to the power of negative n times dy dx, which is your y prime. So du dx is u prime is equal to this new term. Now if you solve for y prime out of this, you just need to divide both sides by 1 minus n times y to the power of n, because this goes there, times u prime. Just very basic algebra. So the clever thing to do was the substitution. Okay, once you do that, things kind of slowly take shape. So let's plug it into this equation now. We have y to the power of negative n times y prime, which is 1 over 1 minus n. Remember that n is not equal to 1. Okay. So you don't have to worry about that case here. So you have y to the power of negative n times y prime, which is being plugged in from here, which is y to the power of n times u prime. You can see what's going on there. Okay. Plus p of x times, this is my u, okay, y to the power of 1 minus n times u equal to q of x. Can cancel these two terms. Suddenly the equation is a linear first order equation. So we have 1 over 1 minus n, which is a number, times u prime plus p of x times u equal to q of x. This is a linear first order equation. It's not the standard form. You should multiply throughout by 1 minus n to do that. Okay, but at least you got rid of the non-linear part here. So this is a linear first order differential equation in u, not in y. Okay. And you know how to solve this integrating factor. Okay, so solve for u. The only thing you have to do later is that you need to recover y from this equation. So solve for u and then y. That is an algebraic process which should be pretty straightforward. So this class of equations, which is pretty special, it's called the Bernoulli's differential equation because he's the one who did it. So we had to give him credit for his achievement. Okay. So we'll do a few examples, make sure that all of you are comfortable with this substitution and this chain rule process. Okay. The whole idea is to convert a nonlinear equation to a linear equation. All right, so for all the problems, please don't try to memorize this and try to just, I'll just go through all the steps for each of the problems, okay, and make sure that it's a nice, smooth process. Any questions about this Bernoulli's equation? In the textbook, I think it's written in a separate section, but I usually cover it in section 1.4 because they kind of belong to the same thing. All right, let's do some examples. Yep. What's that?
If n equal to, we had the standard form where there was y to the n on the right hand side.
Right.
Just erase it.
Oh. So if n equal to 2, is that a request?
N equal to 2 on the right hand side.
Uh-huh.
Does that mean it's no longer linear?
Right. Anytime there is a n which is not equal to 1, it's non-linear for y. Yeah. So when you write something like y square y prime, that's a non-linear term there. Okay. Or e to the power of y times y prime. Okay, that's a non-linear term. So far we have already done linear equations in 1.4. Now we make it non-linear. Okay. But Bernoulli cannot do this one, only this one. All right. Actually, there were two Bernoullis, so you had to first do a search about which Bernoulli actually did this. Both of them were incredibly smart. I think they were brothers or cousins, I forgot. But example 1. Solve, which means find the general solution to x square y prime plus 2xy equal to 5y to the power of 3. Okay, so that is the non-linear term. First thing, convert it into standard form, just like you do in all the problems in section 1.4. Divide throughout by x squared. Okay. So y prime plus 2x over x squared is x in the denominator times y equal to 5 over x squared times y to the power of 3. All right, so let's follow what Bernoulli suggested. Divide this y to the power of 3 throughout. And you get y to the power of negative 3 times y prime plus 2 over x times y to the negative 3, which is y to the negative 2, equal to 5 over x squared. So substitute u equal to y to the power of 1 minus n. N in this case is 3. And it shouldn't be surprising that you see that same term here. Okay, always. That is your u, that is your u. So that's a nice checkpoint there to make sure that you're going in the right track. Du dx or u prime, whichever notation you like, is du dy times dy dx. Du dy is the only place where you have to do some minor calculus. Okay, so du dy is negative 2 y to the power of negative 3. Times dy dx or y prime. And solve for dy dx by dividing both sides by this term. So dy dx is, or y prime is 1 over negative 2 y to the power of 3, okay, because I'm taking it to the left hand side, times du dx, which is u prime. Let me know if you have any questions, okay, or if I'm going too fast. All right, so where were we? Yep. So let me just write that step here once more. Y prime is negative 1/2 y to the power of 3 u prime. So we're going to plug it in here. So it's y to the power of negative 3 times y prime, which is negative 1/2 y to the power of 3 u prime. So when you're doing this, you should get a feel of what you're expecting, right? The y to the negative 3 and 3 would cancel out. Okay, that's where we are doing this. Plus 2 over x times y to the negative 2, which is your u, okay, equal to 5 over x squared. So as promised, these two terms cancel, and then you have negative 1/2 u prime plus 2 over x times u equal to 5 over x squared. That is not in the standard form. Okay, you have to multiply throughout by negative 2. And you get u prime minus 4 over x times u equal to negative 10 over x squared. Now we are back to our comfort zone, right? This is a linear first order equation. That's what we mostly did in section 1.4. Write the integrating factor and solve it. Okay. So your p of x here is negative 4 over x. So the integrating factor is e to the power of negative. Okay. Remember, I think this was the first example similar to this we did in section 1.4. So this is e to the power of negative 4 ln of x, which is x to the negative 4. So you know the drill here, x to the negative 4, not u times, it's not y, it is times u prime equal to negative 10 over x squared times the integrating factor. But a little bit lazy there. I should have written one more step here with the integrating factor multiplied on both sides. Okay, but I hope at this point you have seen enough of that stuff. So after you do that, you have the integrating factor times the variable prime equal to the right-hand side times the same integrating factor. So this is negative 10 x to the power of negative 6. You're dividing by x squared, so it becomes x to the negative 6. Okay. All right. Finish it off. So integrate both sides. X to the negative 4 times u, not y, equal to negative 10. The integral of x to the negative 6 is x to the power of negative 5 divided by negative 5. Okay, you're adding 1 plus c, which is 2 x to the power of negative 5 plus c. Multiply both sides by x to the 4. So you get u equal to 2 times x to the negative 1 plus c x to the 4. So multiply Now you might think we are done. We are not. Okay. Our variable when you started the problem was y, which for some reason I erased what I did with it. What is my u here? Somewhere here there was a u. Y to the power of -2, is it? Yeah. Oh, thank you. So you need to use this to recover your y. So this is y to the power of -2 equal to, you can write this as 2 over x if you want, plus c x to the 4 . We need to get an exponent of 1 here, so multiply this by a -½ so which means that you're raising this also to a -½ so y equal to 2 over x plus c x to the 4 to the power of -½ All right, so that is the process with the Bernoulli's equation. So once you get used to the substitution and everything, it, things get more comfortable. The first time, it's a lot of pieces there. Any questions on this process? All right, can you just take that handout and do the first two problems? So again, it's on Canvas under in-class handouts. I just uploaded this morning. Okay, so I just need to refresh your browser if you don't see it. The last two, I've left it as kind of a homework in this topic, so you could do it later and then make sure that you get those answers I put there. Okay? And if you want help with it, let me know. We'll do the first two in class now. Stop sharing that. That's a y to the -2. Okay, I know the negative is a little faint there, but maybe it's just my eye. So multiplying both sides by y square. Okay. All right, so we have y to the 3 in the right place. So du dx would be 3y square y prime. So y prime is 1/3 y to the power of -2 u prime. So this is y square times y prime is 1/3 y to the power of -2 u prime. No surprises there. And of course, y to the 3 is u. Suddenly I thought, why isn't it linear? So y to the 3 is u. Okay, so this is and multiply throughout by 3 so that this is in the standard form. All right. Let's see if there were any questions. No. Okay, so that's the standard form. Okay, so the integrating factor here is rather straightforward. Since p of x is -15, the integrating factor is just e to the power of the integral of -15 dx, which is e to the power of -15 x. Okay. Nothing complicated there. So it's going to be e to the power of -15 x times u prime equal to 3 times e to the power of 3x times e to the power of -15 x. Once again, when you do these integration steps, make sure that you don't do anything silly. Okay, before you do the next step, try to combine these two into a single exponent. It's not the product of the integrals that you're going to do. Integrate both sides. And you get e to the power of negative 15 x times u equal to, so k is negative 12 here, so you have to divide negative 12, so it's 3 over negative 12 e to the power of negative 12x plus c. And divide both sides by, or multiply both sides by e to the power of 15x. That is easier to say, I think. So multiply e to the power of 15 x on both sides, and you get u equal to negative 1/4 e to the power of positive 3x. That's 3 times e to the power of 15x. And since u was y to the power of 3, you have to take a cube root of both sides to recover y. So that's your final answer. If this is an initial value problem, you have to wait till you get your y before you plug in the y of x equal to 0 equal to something. Okay, don't plug it in for u because that is not the actual variable here. Okay. Any questions on this? All right, let's do that next one quickly, real quickly, and then start chapter 2. So your test next week will cover up to here. Okay. So separable equations and then integrating factor, and the applications are Newton's law of cooling, mixing, and also the Bernoulli's equation, which is just another kind of linear first order equation. So problem number 2 in the handout. Y, it's already given the standard form, I think. Y prime plus 4 over x times y equal to x to the power of 3 times y square. And to avoid concerns about logarithm and absolute value, you're given that x is strictly greater than 0 here. Okay, so we can do the problem without absolute value. I hope these algebraic steps are natural to you. Okay. I know this kind of keeps going back and forth, positive and negative exponents. That's the level of algebraic comfort you need to have in this course. Y to the negative 2 times y prime is negative y square u prime. So don't forget there is a negative in front of the first term. Okay, so it's negative u square plus 4 over x times u equal to x over 3. So when you negate it, what? U prime minus 4 over x times u equal to negative x over 3. Put u prime there, right? Yep. Well, we have the same thing happening here again. So the integrating factor is x to the negative 4. A bit repetitive here. So this is x to the negative 4 times u prime equal to negative x to the 3 times x to the negative 4. Don't forget to multiply integrating factor on both sides. Because I didn't do the extra work there because that is the same integrating factor in the previous example. Integrate both sides. Remember that this is x to the power of negative 1 here. Whose integral is a natural log of x, and we don't have to worry about if x is positive or negative. You know, it's given it's strictly positive. Okay. So if you integrate this, you get x to the power of negative 4 times u equal to negative of the natural log of x plus c. All right, multiply both sides by x to the 4, and you get u equal to negative x to the 4 ln of x plus c x to the 4. Don't combine this x and x to the 4. They are two different entities, so don't write it as x to the power of 5 here. Okay. That's why I write it before, so that you won't be tempted into merging into those unwanted terms. And since u was y to the negative 1, y would be just the reciprocal of u. So y would be negative x to the 4 ln of x plus c x to the 4 to the power of negative 1. So you multiply negative 1 in the exponent in both sides, or you take the reciprocal of both sides, whatever works for you. So officially, that is the end of chapter 1. Up to here for your test next week, not today. I'll try to kind of keep all the test material maximum the Monday before the test, okay, so that you won't have to cover a lot of material that is too close to the day of the test. Okay. So this time you have a lot more window before the actual day of the test here. So we have finished the material today. We've got a whole week now. All right. Any questions about chapter 1 material, or about what you should expect for the test and so on. Again, the length of the test is between 4 to 5 questions. Okay. It's an hour and 10 minutes to write and upload. So I don't give extra length problem or something. So if you are able to do it correctly, you should be able to do it within 35 to 40 minutes. Okay. All right, so let's just start chapter 2. I won't do anything fancy today. The first 2 sections of chapter 2 are a bit of an introductory type. So let me just cover that today, and then we will start actual solving next week. It's a rather long chapter, so be prepared to spend some time here. Chapter 2, second order linear differential equations. So second order, as I mentioned in the first lecture, second order means there is a second derivative somewhere in there, okay, y double prime, or d square y dx square is the highest derivative that happens in the differential equation. There is no third derivative there. Okay. And linear means that all the y terms are not, it's a weird way of saying it, not non-linear, which means that there is no y square or 1 over y, or even you cannot even have the square of the second derivative for that matter. Okay. Those kinds of terms takes it to a different level altogether. So right now we are not prepared to tackle any of those things, right? We'll start with the most basic case, that is linear second order differential equations. Okay. So look like this: a2 of x times y double prime. I won't be using this notation a lot because there's a lot to write. Okay. So y double prime means it's a second derivative, plus a1 of x times y prime plus a naught of x times y equal to some function f of x. That is what a linear first order differential equation, linear second order differential equation looks like. This cannot be equal to 0 to preserve the second order nature of the equation. Okay. All others could be anything. A1 could be 0, a naught could be 0, f of x could be 0. Okay. Of course, these functions have to be continuous and all that so that you could do your calculus. Okay, but apart from that, there is no other major restrictions on those functions. If f of x is equal to 0, we call it as a homogeneous equation. So throughout this course, whenever I bring up the term homogeneous, that means the right-hand side is equal to 0. Even in linear algebra, okay, the same term is kind of borrowed there. So if this was equal to 0, that will be homogeneous. If it is not 0, if it is some function which is either constant or a function of x, it's a non-homogeneous equation. And we'll see applications of all these. So we'll start off with the homogeneous case next week first, and then we will move on to non-homogeneous. Okay, as you would expect, this is easier. That's not easy, so that shouldn't be surprising. So today I'm just going to do sections 2.1 and 2.2, which is just a couple of basic definitions and also what to expect in this chapter. Okay, there is nothing heavy duty going on there. We are not going to solve anything really. So what to expect? You solve a second order differential equation in general. Okay. Remember that when you did the first order differential equation, you had one constant. Chapter 1, all the solutions look like y equal to something plus c. Okay. So it's natural to expect that when you go up an order, you're going to have more constants there. Okay. It's going to have two constants. We'll call it as C1, C2. And one of these could be equal to 0. So to find C1 and C2, we need some extra conditions. Okay. Usually given y of 0 and y prime of 0 to evaluate both C1 and C2. Now, before I talk about the next thing, let me just ask you this. What is the easiest place where you could find a second derivative as an application? The first derivative is a mixing problem and Newton's law of cooling. Second derivative, where do you see it? Yeah, acceleration. So anytime you do the Newton's law, Newton's second law of motion, okay, this acceleration is always the second derivative of position with respect to time. Okay, so if you think that this is not going to appear in real life problems, you're wrong. Okay, it's everywhere, right? Anytime there is something moving, it's a second derivative of position with respect to time. Definition number 1. These definitions are very important because we're going to keep on using it throughout this chapter. Okay, we'll take for granted, but you need to keep that at the back of your mind that this is what is going on. Two functions y1 of x and y2 of x are linearly independent. That's a very technical sounding word, but all it says is that they are independent of each other. Okay? They are linearly independent if y1 of x is not a scalar multiple of y2 of x. This is a very religious thing for us in this chapter. Okay? Anytime a function is a multiple of the other, we are just looking at the same function. We need to have two functions which are completely different if you want to talk about them as two acceptable solutions. Okay? So I'll write some examples, and usually by visual inspection, you should be able to tell me if they are linearly independent or not. Examples: y1 of x equal to e to the power of 2x, y2 of x equal to 5 e to the power of 2x. Clearly, right, I don't have to call somebody and ask, oh, what do you think about these two? Are they scalar multiples of each other? Yes. Okay. y2 is 5 times y1. Okay. So this is what you call as linearly dependent because one is a scalar multiple of the other. When you say independent, they are not scalar multiples. Okay. So in this case, one is a multiple of the other, so one depends on the other. y1 of x equal to e to the power of 2x, y2 of x equal to e to the power of 3x. What do you think about this one? Just by looking at it, do you think these are dependent or independent? Independent. Okay, these two exponents are different, so these are linearly independent. These are two different functions. Okay. If you draw the graph, one of them is increasing steeply than the other one. It's not on top of each other. Okay. So linearly independent. What about y1 of x equal to sine of 2x and cosine of 2x? Again, these are obvious questions. I'm just trying to see if you are paying attention or not. What do you think? Are these linearly dependent or independent? Independent, right? Just because those two twos are the same, okay, sine and cosine are two different functions. It's a tricky one. Y1 of x equal to e to the power of 3x and y2 of x equal to xc to the power of 3x. What about people online? What do you think? Is it independent or dependent? So I got two different answers there. You need to think about what x is. Is x a scalar or a variable? It's a variable. Okay. So 5 is a scalar. This is a variable. So if it is a variable, we are okay, which means they are linearly independent. Later, when we do linear algebra, we will look at a more formal way of doing things. Okay, there's something called a Wronskian, which is actually done in chapter 2, but it's kind of in the wrong place to do it. So we'll do that in chapter 5. Right now, all these things are done on visual inspection. So let's write down the summary of what we just wrote here. So, please remember this throughout chapter 2. Okay. E to the power of k1x and e to the power of k2x are always linearly independent. Is that a full statement, or should I write if? Do we need a condition here? If k1 is not equal to k2. We'll be freely using this result next week. Okay. Whenever k1 and k2 are not equal, they are two linearly independent functions. Two, sine of k1x and sine of k2x, and similarly cosine. Okay. These are the functions we'll be seeing a lot in chapter 2. They are also linearly independent if k1 is not equal to k2. Number 3, sine of kx and cosine of kx are always linearly independent. Okay, because those are two different functions. I don't have to even tell you that they are independent. Okay. For e to the power of kx and xc to the power of kx, not k to the power of kx, that is bad, xc to the power of kx, they are also always linearly independent. And if you combine these functions in any form with multiplication and so on, as long as they don't look alike, they're okay. Get used to these functions because you know these functions, but these will be appearing in pairs when you're starting to solve these second order equations next week. So that's the first definition. Any questions about what linearly independent pair of functions means? Means one should not depend on the other. Not a very creative name, but works. Definition number 2. Okay, this one is super important. Okay. If y1 of x and y2 of x are two going to put a blank here. I'll let you fill it up a little later. So if y1 of x and y2 of x are two blank functions which both satisfy the homogeneous differential equation, a2 y double prime plus a1 y prime plus a naught y equal to 0. Okay, that is what makes it homogeneous. Okay. So if these two by themselves satisfy this equation separately, you can combine those two. Okay. A general solution to this differential equation here, which I don't want to write again, let me just write star. The general solution to star is given by y of x equal to c1 y1 of x plus c2 y2 of x. It's a golden rule of differential equations starting from second order. It's called the principle of superposition. Why is it called superposition? Because we are superimposing two things from two different places. Okay. Principle of superposition. It says that if you have some functions, then the scalar multiple is also an automatic solution to the same equation. Okay. This is also a solution, and you can combine them. That is also a solution. Okay. Provided, what is the golden pair of words here? What should be the condition on the functions? They should be linearly independent, so that you are looking at two different functions. Okay. You don't want to count the same function twice, thrice, and so on. There should be two linearly independent functions. Oh, word, independent. Then if you just start multiplying each of those functions by some numbers, okay, you just keep on generating an infinite number of solutions. That is going to happen for all homogeneous second order differential equations. So let me show you a couple of examples, and then we will wind up. We're going to use that throughout chapter 2. Okay. You get two functions, just put it into the general form, you get the general solution. Example, verify that y1 of x equal to e to the power of negative 2x and y2 of x equal to e to the power of negative 3x. Satisfy the differential equation y double prime plus 5y prime plus 6y equal to 0. Okay. Don't forget these are two linearly independent functions, okay, because negative 2 and negative 3 are not the same. So first, verify that each of these satisfies that equation, and then write a general solution. So I'm not asking you to solve this. We don't know how to solve it right now. Okay? We'll learn that next week. Right now, all I'm asking you is just plug it in and see that it's equal to 0. So it's a exercise in calculus 1, if you want. How do you do it? Take each function, find its derivative, second derivative, plug it in, simplify. So y1 is e to the power of negative 2x. So y1 prime is negative 2 e to the power of negative 2x, and y1 double prime is negative 2 times negative 2, positive 4 e to the power of negative 2x. You're doing derivatives now, not antiderivatives, so multiply those things. The question is, I don't know whether y1 double prime plus 5 y1 prime plus 6 y1 is equal to 0. I hope it is. So y1 double prime is 4 e to the power of negative 2x plus 5 y1 prime is going to be plus 5 times negative 2. That's going to be minus 10 e to the power of negative 2x. Plus 6y, which is 6y1, that is going to be plus 6 e to the power of negative 2x. Okay. And you add them, you get 4 apples minus 10 apples plus 6 apples, 0 apples. So yes, it is a solution. Can you do the second one quickly? Chop, chop. So I haven't posted the solutions for 2.1 and 2.2 because you see problems like this, you could do it yourself. Okay. So y2 is e to the power of negative 3x. Not leaving enough room here, but okay. Y2 prime is negative 3 e to the power of negative 3x. Y2 double prime is 9 e to the power of negative 3x. And am I out of time? So if you plug it into the equation, you get 9 e to the power of negative 3x plus 5 times y2 prime, that is going to be minus 15 e to the negative 3x plus 6 y2, which is plus 6 e to the negative 3x. No surprise, and that is equal to 0. The good thing is these are the only two functions that satisfies this. If you plug in e to the power of negative 4x, you're not going to get this. So for some reason, these are the only two solutions. We'll find out why on Monday. So based on these two functions, which are linearly independent, we can write the general solution using the principle of superposition I wrote there. So this is your y1, that is your y2. So general solution y of x would be c1 e to the power of negative 2x plus c2 e to the power of negative 3x. That is what superposition tells you. It gives you the freedom to combine these, which means that if you have two functions, then any multiple of the first one and or any multiple of the second one will satisfy this equation automatically because the scalar will just multiply it out. It's a homogeneous equation. The right hand side is 0. So on Monday, we'll find out how I got this negative 2 and negative 3 up here. What kind of magic was that? Okay. So we'll start solving this on Monday. Here is the golden thing I want you to know. Remember this from high school? Memories come back now, right? How do you solve? What is the formula for the roots for this one? Negative b plus or minus 4ac over 2a. That's what it is. Is that right? No, completely wrong. So how do you write it? Negative b plus or minus square root of b square minus 4ac. Now it's right? No. We are kind of done with use of calculus in this course, believe it or not. Okay. Going to depend on this guy a lot next week. So if you've never seen the quadratic formula, please talk to me. If you've forgotten it, go review it. Okay. We need that over and over. All right, it will be a good point to stop. Have a nice weekend. Nothing to worry about for this weekend. Okay. But just if you have not started doing your homework, please do that and catch up with the material. And I'll see you on Monday. We'll do section 2.3 on Monday. All righty.
Thank you.
Thank you very much.
Thank you.